All right, so now let's talk about some other features of E2 reactions. Most importantly this is going to be, again, this stereoselectivity. We talked about stereoselectivity with the SN2 reactions. It's an important part of our E2 reactions too. First things first, remember, more stable. If you can form two products, the more stable one is going to be the one that forms in the most abundance, the major product. So for example, here I have this, what is this, 3-bromopentane, treat that with a strong base. I can get either the trans or the cis product. And remember, the trans product is more stable because I have these big bulky groups on either side. Okay, so in terms of stereoselectivity being either cis or trans, the trans in this case is more likely to form because the big bulky groups are on opposite sides. Okay. Unfortunately, with the E2 mechanism, it can be a little bit more of a pain in the butt than that. So when your beta carbon has 2 hydrogens, then you just need to think cis and trans. When it only has 1 hydrogen, there's actually only going to be 1 product that's formed. Okay, so let's take a look at this at an example here. Notice here that if I'm going to go in and pick my beta carbons, that's this carbon here and this carbon here. Only one of those has a hydrogen, right? So this tert-butyl group isn't going to be in consideration at all. So it turns out that if you react this particular species, you only get this product here, and none of this is formed. And yes, this pH, by the way, pH represents what's called a phenyl group, which is basically a benzene ring separated by a single bond. So yes, it's true that in this product where nothing's formed, this is a big bulky group, and this is a big bulky group. So that product's kind of going to be sterically unstable anyway. But that's actually not why none of it's formed at all. There's something even more important going on that's going to lead to only this one product, okay? That is the fact that all 4 atoms, the halogen, both carbons, and the hydrogen all have to be what's called coplanar, meaning they have to lie in the exact same plane for an E2 reaction to occur. Why is that? Well, let's remember what exactly happens in an E2 reaction. You have this base. It grabs this hydrogen, and then, very importantly for an E2, at the same time, this new pi bond is formed, and you have that loss of your leaving group, right? Because all these are happening at the same time, remember the nature of that double bond that's going to be formed, that pi bond that's going to be formed. You have these 2 carbons, they're linked by a sigma bond. The pi bond that's formed is between p orbitals on either of those carbons. So this pair of electrons is coming down, is going to be a bond between the p orbitals in that carbon. This bond that's breaking here. So basically this used to be an sp3 and then it has to become a p orbital. Likewise, this bond here used to be an sp3. You know, the lobe of the carbon that was being used was an sp3, and now it has to become a p orbital. So all of those have to be perfectly in line in order for this transition to happen, okay? Bottom line is the halogen and the hydrogen have to be coplanar or in the same plane. We can illustrate this really easily, what I mean by that, using our Newman projections, right? So we have this Newman projection here. By coplanar, I mean all of these atoms lie in the same plane. That's the only time an E2 elimination is going to happen, okay? So this has big implications on the stereochemistry. There are 2 possibilities of how these could be coplanar. One is they could be in this staggered conformation, but I could also rotate about this carbon-carbon bond right here and put these in the same plane as is illustrated here. Well, what's the problem with this? Again, if we go to our Newman projection, This is this eclipsed conformation. And we know that the eclipsed conformations are way less stable than these staggered conformations. If we remember, we had these rotational, so this is energy, and this is dihedral. They always look something like this, where the peaks were at the eclipsed and the valleys were the staggered, right? So they're not going to spend time on the peak. Those are the least stable. They're always going to fall into one of these staggered conformations. So basically, elimination doesn't happen when they're in the eclipsed conformation. It will only happen in the staggered conformation. And that has serious implications on what the stereochemistry of the alkene is going to be, right? So if we imagine, again, high energy rotamer, or another way of saying rotational conformation. So this isn't going to happen. It's only going to be in your low energy staggered conformation. And so then what happens when these are eclipsed, this group gets eliminated, this group gets eliminated. And so these will be on the same side, right? In this case, your phenyl group will be on the same side as the hydrogen, and the tert-butyl group will be on the same side as the methyl. This is a Newman of an alkene. So the only alkene that will be formed in this particular case is this one here. There's no consideration of like, well, which one of these would be more stable or blah, 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 because there's only one possible way that the bromine and the hydrogen can be lost from the same plane in this staggered conformation. Okay, so then let's take a look at a few of these here. So what's going to happen? Again, as these are drawn, it's actually kind of nice because the bromine and the hydrogen are in that staggered conformation. But then let's pay attention to what happens to these different groups, right? So in this case, R1 and R1 are both pointed at me. So that means that they're going to be on the same side at the end. I guess I can use the red to... Once that that alkene is formed. Likewise, R2 and R2 are both pointed into the board. I can be even better about this by, sort of prove this by drawing the Newman projection of this particular structure first. Right, so the hydrogen's down. Right, so again, you have these R1s are on the same side importantly, when you're in the staggered conformation, and so they're going to be on the same side of your double bond. Likewise, over here, now R1 is pointed out and R2 is pointed out, so this would lead to some structure where it's consistent. R1 and R2 versus R2 and R1. And again, I can sort of show using the Newman projection. Now we have R1 and R2 on the same side, and so that's how we got it over here. Okay, now that's all well and good when it's drawn in this very simple way. Unfortunately, rarely are we going to put the bromine and hydrogen on a straight line and the other groups on dashes and wedges, right? So let's make sure we know how to do this with our normally drawn bond line structures. So by that, I mean something, we almost always keep the alkene, the the carbon backbone of the alkane is what's in the plane of the page. And our substituents would be like our bromine coming off or a methyl group coming off. Right, so now how would we figure out what the product of this is? Again, this beta carbon only has one hydrogen. So I got to be careful because I can only, potentially, at least from loss of elimination of this hydrogen, I'm only going to get one product. So you can actually, in this case, it's kind of best case scenario because the hydrogen's pointed into the page. So my bromine and my hydrogen are indeed already staggered. Let's just prove this though by drawing the Newman projection, right? So again, we got these Newman projections rearing their ugly heads. So I'm looking down this bond just to be clear. So here's a CH3 pointed out this way, that's my bromine. This way is going to be a hydrogen. And then if I'm looking at the back carbon up, I have my ethyl group. Down here is a methyl group. Over here, on my back carbon is my hydrogen. So again, I indeed have my carbon and my bromine and my hydrogen are coplanar. Awesome. So that means that these methyl groups will find themselves on the same side, and this ethyl and hydrogen will find itself on the same side. Okay, so if I draw that, where this represents my front carbon. Okay, so, and again, this is the only product that will be produced in this particular reaction because we only have the one beta hydrogen. If you were being good, you also have these beta hydrogens to consider, so you would also have as another product but which one of these is going to be your major product? I guess I didn't tell you a base, but let's assume that it's something tiny like hydroxide, then this would be the more stable and thus your major product. Okay, so this is a really important process, is understanding the stereospecificity of these types of elimination reactions. Let's just do another example, just when the hydrogen isn't automatically pointed backwards. So now we have a similar one. But now our methyl group is pointed into the board. So how would we do this? Again, thinking about it in a Newman projection. But now the methyl group is pointed over here. My ethyl group is still up, and the hydrogen. So as it's drawn, there's no elimination reaction that will occur in this particular rotational conformation, right? Because this hydrogen and this bromine are not coplanar. So instead I have to rotate to make them coplanar. This was a big thing before. Do you rotate the front or the back? Really doesn't matter. You just have to be consistent or rotate correctly. Just like before, because this is what the book does, this is what I'm going to do, which is rotate the front carbon. You just have to make sure that these three groups all switch positions here, right? Actually, let me just do a different color. So that means I'm going to start off, just going to draw my back carbon the exact same. And now I have rotated it. Now these are coplanar, my bromine and my hydrogen. So now this elimination can occur, but now notice that these methyl and ethyl groups are on the same side, and then methyl and hydrogen are on the same side. So the products here Sort of not leaving myself a ton of room. Would be double bond with your methyl group on the same side of your ethyl group. If this is my front carbon. Okay, and again, you would have the other minor product as well, but this is the more highly substituted and thus the major product. All right, so pain in the butt. Stereos, thought it was bad with SN2 with the inversion. It's even worse with E2, right? The stereospecificity, because you have to consider the fact that the hydrogen and the bromine, or whatever the halogen is, has to be coplanar in order for the elimination to occur. When you have two hydrogens, you don't have that same problem where there's only one product. There may be two products, and then it's all about consideration of where your bulky groups are, right? So let's say that R1 was some big, ugly, tert butyl group or something like that. And R2 was a big bulky phenyl group. And R3, I don't know, a methyl group, something like that. Right, so again, because you have two beta hydrogens, both of these are going to be products, but then you're going to have to take a step back and look at which one of these is going to be more stable based on sterics, right? So in this case, this would be my major product because this is a big group and this is a big group, and so I want them to be as far away as possible, okay? When you have one beta hydrogen, then you have to really do some work in order to figure out what that product's going to be. So there's only going to be the one. If you have the two, you can sort of draw them both out and figure out which one's going to be the most stable based on that simple principle of decreased steric hindrance, meaning big groups want to be far apart. I sort of was throwing around these words, stereoselective and stereospecific, so I want to be clear on what that would mean. Stereospecificity, the key word there is specific, meaning if you start with one particular conformation, so for example, R, and then you would get S at the end, but if you started with the other one, you would get R. You could do the same thing with our alkenes, where it would produce either E or Z, but not both, right? So an R would produce Z, an S would produce E, something like that. That would be stereospecific. Starting out with one specific stereoisomer, or starting out with one stereoisomer gives you a specific stereoisomer on the other side. Stereoselectivity is when, for example, the E isomer is more stable than the Z isomer, and thus you get more E, right? Or another EZ, or we also say like the trans isomer, because both groups are both big groups are on either side, is going to be more stable than the cis isomer. Okay, so stereospecific, you get a very specific stereoisomer out of it. Selective just means that it's going to produce the more stable of two different stereoisomers. Okay. So now with rings. Rings are an extra super bad case when we talk about E2 reactions, and that's because rings can't rotate freely, right? They have basically two conformations, the two flips. And elimination is only going to occur when that halogen is in the axial position, right? So in this case, we have chlorine in the axial position that can be eliminated from that hydrogen. If we do the flip, that won't occur, right? Because they just aren't coplanar anymore. Even though this is the more stable of those two conformations. All right, so this is just another consideration. It will potentially be slower in a cyclic alkane because of this. So let's look at these two examples here. Again, what's really important is that you have to have a hydrogen on the other side. So one of these two won't be able to undergo an elimination reaction, period, right? And that's this one over here, because on either of those beta carbons, so we look at our beta carbons, we do have a beta hydrogen, but they are on the same side as that chlorine, which means that they'll never be able to be coplanar. You'll never be able to get them, you know, basically trans from one another, although trans isn't a good word because it's a hydrogen. But nonetheless, they will never be able to be coplanar for one another. So this would not be able to undergo any E2 reactions. Okay. This one, however, because you have this hydrogen over there, you also have this beta carbon, which you can pull from, but nonetheless, will actually be able to undergo these E2 reactions. So drawing your chair conformations is going to be really important for determining whether or not a cyclic alkane will undergo an E2 reaction. Okay, and so let's just go for it here. Show what I mean. We want the chlorine to be in the axial position for this to happen. All right, that means that that methyl group is in the equatorial, and you have a hydrogen down there, right? So here we will have an alkene product that's formed, a cyclic alkene that's formed. I guess let's just put it in the same place just for clarity. This product will form. Now, you can also have it, you know, this has two beta hydrogens, so you're guaranteed to have one that would be potentially in the other position. So now, I guess let's just color code this carbon here. I'm talking about this one here. So there's a hydrogen pointed down, so I can also have this product. But which of these is going to be my major product? More highly substituted, right? So this is my major product, right? So that's why this is such an important consideration that you have to make, is the, you know, the relative position, axial of your halogen, but also the neighboring carbon on the, or the carbon, I'm sorry, the hydrogen on the neighboring beta carbon. And then the last thing is with regard to the chair flip, remember big groups don't like to be in the axial position. So even though we have this beta carbon here that has these hydrogens, if we drew the chair conformation, we would see that when we put that tert-butyl group in the axial position, in the equatorial position, which is where it's going to go because it's so big and bulky, that means that my chlorine on my neighboring carbon is also, I guess I should do it same direction, is also in the equatorial position. And reactions can't happen. E2 reactions can't happen when they're in the equatorial position. So even though we will get formation of the product and we would only have one product that's formed, it would form very slowly because it would require a chair flip that puts that big bulky tert-butyl group into the axial position. Likewise, down here, we can see that it would happen, and it would happen quicker because if I drew my chair conformation, bad chair. When the tert-butyl group is in the axial position, that means that the chlorine kind of messy, would be in the equatorial position. right? Because they're both on the same side. So that's great. That means that this reaction would happen readily, would happen quickly, and I would get a mixture of two products. Which one is going to be the major product? Again, the more highly substituted one is more favorable. Okay, so again, drawing the chair conformations is going to be important for this particular chapter, being able to figure out, putting your substituents as being either cis as they were up here, no, that was a lie, as being trans as they were up here, or cis as they were down there. Being able to fill in those locations correctly is really important.